Hey, what's going on, guys? Games here. So last video we ended up with being able to write a single byte the given physical address into the random access memory, right? And the purpose of this video is to create the main routine, the main editor loop, to do two things. So the first thing is we need to initialize the address of where are we going to write our bytes. And the second part is we want to write the actual bytes at the given address, and no matter how many bytes we input there, we can input 512 bytes at once, or just 16 bytes or 32 bytes to fit like half of the line or the entire line. So or even input just a single byte. So that's pretty it. So we got plenty amount of work to do here. So yeah, without further ado, let's actually start writing some code. Okay, so yeah, let's get rid of unnecessary stuff here. And before anything else, I would like to define a couple of constants. So we'll need a scan code for enter key, and also for escape key as well, because we're going to be relying on enter key to actually like go to the next iteration of a loop. And if we want to write, if we just ended up writing on the current memory address and we want to start writing from a different memory address, or if we want to check to fix something that we've entered run in the current iteration, so we'll need enter. And escape is going to be needed to escape back from the editor loop back to the shell. So I just want to define escape key here and 0x01, and this is the escape scan code. Okay, so what else? I don't need this stuff anymore, so let me get rid of this. Okay, so yeah, here we still will keep this print memory, so initially print hex dump. So this is still on the cards, and here we will create so here this is going to be main editor loop. Okay, so we just enter right over in here, so edit loop. All right, and I just want to make sure you don't have any redundant information here. Okay, so yeah, and we want to jump to the edit loop. So from now on, we're no longer able to, jump into console, and we should stuck in the editor, which is okay for now. Yeah, great. So the very first thing to consider, so first we will initiate a few so first we need to initialize the address, the right address, this one, which would be in the range between this 500 of hexadecimal and up to this value plus 32 bits more. So just to specify where exactly we're supposed to be writing to memory. Okay, and the way I'm doing this is very straightforward and really easy to understand, but probably not the best ever from, I don't know, from the code beauty perspective, or I don't even know. But anyway, just like we've been relying on dx to, like dh and d1 to encode the first and the second nibble for a byte, we're going to be doing a very similar but a slightly different thing to encode the entire right memory address. But here we have a word, not a byte. So instead of writing a custom function to like encode word, instead of encode byte, would actually dump everything into the loop on its own. Again, maybe not the best ever solution, but I think that should be just okay. And probably later on we could probably even just put it into a separate procedure potentially, but no, probably not, because just there are not really enough bytes for that purpose. So, okay, anyway, so we want to, first we want to reset the X register, and the DX register is gonna be used in order to temporarily hold our address. So eventually we're gonna be initializing the AX register from the DX, and then we'll run the store single word instruction to write whatever we have at the AX to this memory to this variable, okay, to the right address. All right, so let's just keep going. So the X register serving as a temp storage for a right address variable. Okay. Yeah, let's get rid of this one. Then what? Then we actually want to print the prompt. So let's say move to ascii. I want to move the prompt, and point ascii to prompt variable. We don't yet have that. We'll now create it and call print string. Here we want to print the prompt. Okay, so the prompt, let's create a variable called prompt and define byte. So the prompt would look like this, exactly like this. Okay, so like hexadecimal specifier, and then 4 digits for address would be used, and let's end with a 0 terminating character. So now we would be able to print the prompt. Okay, and by the way, yeah, I think we can already test that. I think we should be able to test that. So let's go edit. Yeah, and as far as we're stuck in the infinite loop, not taking the input, it just goes forever, which is not really that great, but yeah, that's exactly how it should behave at the moment. Okay, so then what? Then we need to take then we need to have 4 nibbles, exactly up to 4 nibbles to represent this address. So 4 keystrokes, so 4 ASCII characters would then be manually encoded to this hexadecimal value, right? To this hexadecimal value, and whatever address we pick up there, it would get stored into the right address. So later on we could point di to the value at the right address. So later on when we're going to be writing the bytes, they would, just to make sure that the bytes would be written exactly this memory location stored at di register. Okay, when I end this sort of a thing and start demonstration, it would be really easier to figure out how it works. So yeah, so I need to say move to AH hexadecimal 00. So this is the BIOS code to accept user input. How did I did the better commentary somewhere to take to get user input character. Let's make it like this. Oh man, I had a better description for that. Oh yeah, that's much better. Read keystroke from a keyboard. Yeah, that's a much better description. So read, yeah, the keystroke from a keyboard, a single keystroke, right? And 0x16, this is the interrupt to actually, we want to read a single keystroke. By the way, is this? Yeah, create a single keystroke. So we're going to be doing this up to 4 times. Again, we could have done this within the loop, but yeah, I just and yeah, probably I don't know if we have a few free bytes, then we'll probably move this to a separate routine just to make the code look a bit better. But for now, let's just dump everything to the edit loop. Okay, so now if we run it, it no longer be infinitely print and stuff. It would be waiting for a user input. So here is the shell, and now it just waits only for the one, and then just goes back to shell, which is not exactly the case. So we need to print the character and so on. Okay, so but yeah, before anything else, we need to know that if the user actually just pressed escape, that we want to return back to the shell. So we can compare whatever value at AH. So at H, the key code, the scan code is stored. So compare it with the escape key with this value 0x01. So did user press escape and jump equals to return? If so, go to return. Okay, and jump equals edit loop. Sorry guys, yeah, the reason why I'm confused that we actually need to provide the return label here, but now we would anyway gonna jump in here as far as we don't have anything else, so no matter if escape is pressed or not. But yeah, anyway, here we want to print a new line, so move ascii and the new line. So point ascii to new line variable, okay, and call print string. So here we want to print new line, because when we escape from the program, we want at the very end we want to print the new line, and here we want to jump back to shell. So jump and shell segment. Jump shell segment at the offset of 0, so return to shell. Yeah, but currently actually whatever key I press, it would be returning to the shell. Yeah, because we just don't have any logic down below there. So I just pressed not escape, but somewhat a different one. With escape it also works, but yeah. So call, print it just to print the new line, otherwise it would be just there. So yeah. Okay, I could have printed a couple new lines, but yeah, let's just keep it as is. Okay, so what's next? The next thing we want to type, so whatever digit we've just typed, we want to print it on screen. So I say move AH 0x0e, which is the bias code to output character to screen. Okay, we had this before somewhere. It doesn't matter. Okay, just be grabbing it from here. I put and int hexadecimal 10. We actually want print, let's say echo character to screen. Well, let's say print current character to screen. Okay, save. Yeah, let's just give this jump here instruction. So just to give you an idea that if we type whatever but escape, we just stuck. Okay, but if we type edit. If we press escape, then we go back to shell. So now I just pressed escape. All right. So yeah, but let's move further on. So we've just processed a single digit. So the next thing to consider, we need to take care of actually encoding this to hexadecimal digit, to integer, like this ASCII to hex is going to be on the cards now. And we also need to encode not the byte but the entire word, serving the purpose of storing the address where exactly in memory we're going to be writing our bytes to. Okay, so now we want to call ASCII to hex, and by this action we convert ASCII character typed by the user to integer or hex. Let's say to hex value. Actually, literally to integer, to byte, to let's just say to be more precise, to first nibble. This would be the verb first nibble. There would be up to 4 nibbles. So in a byte we have 2 nibbles, the first and the second. In a byte we'll have respectively 4 nibbles. Okay, 4 nibbles in, because 2 bytes and 2 nibbles per byte, so 4 nibbles per word. Okay, so now we need to do the following thing. So I say, so we're going to be using the DH, and remember we did reset the entire DX register, so now we're free to use both the DH, the higher 8 bits, and DL, the lower 8 bits of the DX, of the 16-bit DX register. So DX, we move to DX the value of AL. So here we move first nibble from AL to DH. Okay, and now we need to encode the first nibble. So if I simply say shift left and the DL and shift left to 4, this is exactly the same thing what we've been doing within the encode byte, but we've been doing this with the DL, not with the DH, because we're using just the lower part of the DX. Okay guys, just hold on a second, I need to handle my cat. Sorry guys, I just got 5 cats, and one wants to get out, another one wants to get into the house, the third one wants to eat, the fourth is playing, and I'm going completely crazy because of this. I'm sorry for that. Let's get back to our nibbles. So yeah, encode byte. So we've been working with the DL, which is the lower 8 bits of the DX register, and we're going to be still relying on that. But as far as we're storing the word, 16 bits, so we'll use the entire, we'll use the entire DX register, and just probably the visual representation would make it better. So here we want to encode first nibble. So this is the DX register, and this would be like 1 2 3 4 and 1 2 3 4 1 2 3 4. So this is the DX register. Okay, this is the DH. Okay, and yeah, probably I can say it's just to make it even more clear. So it contains of DH and of DL, like this. So just this visual representation is really helpful to understand what's going on here. So yeah, so DX, there's DH and DL. So now we're dealing with the, sorry, what have I done? DH, not the DL. So DH, left shift by 4. Okay, yeah, left shift by 4. And this is the value that we have eventually. So I'll just be reusing this schema here. Okay, and now we can move on to processing the second character. So yeah, now we want literally to do the same thing, a part of, yeah, so actually I can grab the entire part here, everything but this. So same thing, so waiting for a second keystroke, okay, and again calling convert ascii. And now when it comes to encoding, so did I specify the number? Nope, I didn't. Yeah, and now we need to bitwise OR dh with al, which would result, I will now show what, so move dh. Yeah, so yeah, this happens once, okay. Yeah, this happens once. Then we just OR in. Okay, yeah. Yeah, why did I say encode first, second nibble? Can't encode first nibble, yeah. Copy, and here we actually do encode the second nibble. We don't need to move anything because we just use the XOR operation, and this would result in this schema. So now we have the upper 8 bits of DX register being encoded with a value of a byte that we've composed of out of up to 2 ASCII characters. Okay, and now we need to do the same thing but for DH. Okay, and now we really need to be careful to do so. So I just copy this part, go down, paste, we don't need escape, and now we're gonna be doing the same but with a DL register. Okay, yeah, so here we move the third and convert the third nibble. So here this is already being initialized from the previous part, and now we have the upper 4 bits of DL containing the value of AL. After this, first it goes here, then we shift left, it gets here, and finally we need to bitwise OR the last character with the lower 4 bits of a DL. So yeah, we did work with DH here. So yeah, DH, and OR, and here copy. Oh, sorry, nope. This copy. Yeah, so DL convert fourth nibble finally. Okay, I'm sorry guys, it's not really the most clever way ever of doing things, but this is pretty straightforward and it seems to be working nicely for the purposes we want. All right, okay, so yeah, I really hope this is just kind of fine. Yeah, and finally, now when we did process all the 4, so first, second, third, fourth, okay, DL, and now when we've done all of this stuff, we can now initialize the entire AX in order to, using the single command, the single instruction store single word, write whatever address we eventually have to the right address, to this one. Okay, so step by step. So move to AX, I want to move the value of DX. So by this time DX contains the address, so we want to move entire, like completed right address from dx to ax, because store single word relies on ax. Okay. And now the next thing, so we need to say move di to the right address. So here we want to point di to the address of right address. So now di, after this operation, after this instruction, di points to this address, to this variable. So if we now call store single word, this value would become the value of whatever we have in ax. So that's how the store single word works. Okay, so yeah, now we just need to say store single word. So now we want to write value of ax, and this is the right address, to right address variable. Okay, and now the next thing, which is also really important, we need to say move di. So now we want to point di to the value, whatever value we have, and the right address. So here point di to the physical RAM address to write bytes to, stored in right address variable. Yeah. So what's the difference? This is one of the most essential differences, guys. It's very important. So what this line does, so here di starts pointing to, so in assembly, when we have a label, so this read address is just a label, and by the way, this print string is also the label. Well, here it's implicitly defined as the label, like with this colon, but from the machine code's perspective, there is no difference that much. So we have just the certain address in the memory we can jump to if needed, right? Or we can call it, and the variables are literally also just labeling the address of where. So let's say we want to have this value, right? So where in the memory do we need to look for in order to get this address? We need to look at here. So we can say that read address is kind of like a pointer. So this label is like under the hood. This label is the address of where this value is stored. Okay, so that's important, right? And this value in particular is actually where we want to write the bytes. Remember, like from the previous part, we wanted to write the bytes to the certain location in the physical memory. So the next idea is to point di not here, but here. So to point here, we need the value at here. It's the read address, and we're dealing with the write address. So first, di points here to actually, by using the store single word, to write this address, and then this address would be having, like, say, one of this one in range from this one to this plus 32 bits more. So let's say here after user input we have here like this value, and we need to initialize di being equal to this. It's just like we say move di and 0x500. So in order to make an action similar to this, right, we just say move di and the value of the right address. So that's why these square brackets are used, because we are looking not for the pointer, but actually for the value this pointer is pointing to. So that for the value, this which is available under this address. So I hope that's clear. Okay, So that's the reason why we want to point di to this kind of write address. And now a few more things, just to give a user an idea that this process has been finished successfully. Let's print a colon and reset the dx for the further purposes of encoding the bytes, because there the dx also should be, we should reset the dx there as well. So let's say move ascii, and let's call the variable colon and call print string. We don't yet have this variable, we'll now create this. And after everything else, we want to reset the dx back to 0. So here reset dx again, to be used later on. Okay. And here we want to point ascii to colon variable. And here we want to print colon on screen. All right, so yeah, I think that we can now get rid of this spaces, right? So, and what I wanted to, I was thinking to move this entire part into a single function. So if we don't run out of 3 bytes, then we'll definitely do it, because after cleans up, it should be a bit slightly bigger. So we need to the colon variable. So here let's define colon, define byte, just colon and space, and the new line, and the 0 terminating character, I'm sorry. So currently, guys, what is gonna be happening, okay, what is currently gonna be happening, so let's make it run shell. So do we have any errors? We don't, great. So go into edit, and let's say I say 0550 like this, and it prints the colon, and well, it just jumps to the next iteration of the loop, which is natural because we didn't yet provide the second loop to loop over to make user enter in bytes. But at very least, we may assume that from now on di points to this exact address. So if we now start writing the bytes, it would start writing them appropriately here. Okay, so we're not going to be wasting the time to check this out now, and we'll go strictly forward to implementing the loop to actually allow the user to print the bytes and heavily rely on this encode byte and this ascii to hex that we've created, like this helper procedures. Okay, guys, so here the next essential loop, so let's call it traditionally next byte, and here it's gonna be pretty similar. So we say, I can actually grab it from here. So we take a user input, okay, we take a user input here. We want to ask again, like, whether this is the escape button or not. So if this is the escape, we want to return. It's pretty similar. For now, it's pretty similar. I know it's a bit of a duplication, which is generally not a good idea, but that's what we currently have. Okay. And also, so this is the case if we just want to escape, and there is another condition. So let's say the enter has been pressed. So we want to compare AH and the enter key. So did we already encode the value for enter key? Yes, we did. So did user press enter? Did user press enter? And if so, we want to jump equals to the next line. Line. So if so, If so, then process next line, next input, next line input. Okay, process next line input. We don't yet have this label. Well, we can actually create it here. So let's create the next line. And all we need to do within the next line is just to print a new line. So move ascii new line. Yeah, point ascii to new line variable. Okay, call print string, print new line. So it's very same stuff all of the time. And then we want to jump to the edit loop. Okay, to the edit loop. Repeat edit loop. All right. And by the way, guys, I don't even know, probably, do we actually need this loop in this case? Probably we don't. So I didn't yet test this, so we'll play around with commenting out this one, because probably I believe that we can escape from the next byte only in case if we press enter, and then we go here, so we don't even need this one, and that's how we can save a couple of bytes, I believe. So yeah. For now, I'll just keep it, but later on I'll probably play around with removing this to see what happens. Okay, so if enter key is pressed, then go to the next line, and yeah, print a new line and jump to edit loop. Great. So let's go on here then. Okay, so now we want to output the character to the screen. So whatever byte that user did input. So this one. So if it wasn't enter, if it wasn't escape, then most likely was the byte that user wants to input, right? So we want to print that. To screen. So echoing the character, right? And then what? And then another exception. So we want to compare. Whatever we have at the AL, so we want to print this no matter what it is. But in case if this character is actually a space, then we don't want to encode anything, because if we want to encode, let's say white space, we'll just use 32, or in hexadecimal. Well, we'll need to convert that to hexadecimal, but it doesn't matter. So we don't want to encode the white spaces. So did user enter white space? If so, we don't want to encode it, so we want jump equals to the next byte. If so, don't process it, don't encode it, don't encode it, and process next byte, next keystroke. Okay, and otherwise, if it's not white space, then we want to increment the DH. And you remember that how did we use DH within the encode byte? So it would be either white, or either 1 or 2, depending on whether this is the first nibble or the second one. So here we want to let encode byte know whether this is the first or second nibble. That's essentially what this increment does. And so this would be incremented like forever, but if we have the second, if we have DH equal to 2, then we would reset the DH, right? So that's why the DH might be either 1 or 0. So let encode byte know whether this is the first or second nibble. All right. Yeah, and then we want to call ascii to hex. So we want convert nibble from ASCII to byte. I could convert user input character from ASCII to nibble, whatever first or second. Okay, and then we want to call the encode byte. So call encode byte. Yeah, and encode user byte. Okay, and jump to the next one. Yeah, jump to the next byte, and that's pretty it, guys. That's pretty much it. Process next byte. So if I did everything properly, we now should already have a working hex editor. And if we have a few free bytes, we'll try to move this entire stuff to encode word. So here we have the encode byte, and we'll create another one encode word if we have enough space to implement that. If we don't, then we'll just leave it as it is. Okay, so run edit, and I hold my breath, and let's try to type this A4 that we tried at the address of 500, and if I did everything properly, it should do that actually. So 0500, and now it asks me to enter the bytes. Well, I can actually add more. So if no matter how many spaces I inputted, this shouldn't matter at all. Then let's say 4 Fs, and then let's say have 4 1s. So this should be like A4 F F F F 1 1 1 1. So let's have a look. Oh, whoa. Something that's gonna horribly run. Oh, that's because I forgot to print. Yeah, I forgot to print the memory. Hold on, guys. Just need to make sure where exactly. So yeah, in the print new line, in the print next line. Yeah, so we just print the new line also. Yeah, before anything else, I need to call print memory. Yeah. So here print hex dump. Okay. Run again. Edit again. So 0500. Let's say A4 F F F F 1 1 1 1. And here we go, guys, and we got a working hex editor. Can you believe this? Great. So let's say I want to, so this is 500s. So this FF should be 500.01. So if I say 0501, and let's say I want to put zeros there, so now it should this byte should get resetted. Yeah, and we do this. Okay, now let's say we want like 16, we have 16 bytes. It's the half of the line, and another 16 bytes, another half. So let's say we want to so the like 17th byte. So here, so I can say 0x530. Oh, just hold on a sec, just got something horribly wrong. So let's go for edit again. Yeah, by the way, if we drop back to edit, the bytes are still there because we didn't do anything to them, so it's good news. So I just said 0x, I shouldn't be doing this. So just 0530, and let's put there like C. So here in the middle, starting from in the middle, and 4 digits should become C, and it is. And that's pretty it, guys. That's pretty much it. So now we can, just the proof of concept, just the proof of the fact that we have with the reason why it works. So it also ensures that the logic for encoding the write address, the first four enables for the write address works properly, because otherwise we wouldn't see this bytes being printed at the proper values. So we know for sure that the encoding the address also works perfectly well. But to make like absolutely sure that it works, we can go for another comparison. So let's now go to the online emulator. Let's go to the online emulator and choose the file, right, and go into GameOS tutorials part 16, this one, open, and I'll just write some random bytes there and get the memory dump. And so let's go to edit. So let's say 0500, we want to say A4 and FFFF and 1111. Okay, and then let's say 0530 CCCC. And now, in order to make sure that this actually works properly, well, it does work properly, but just to ensure, we'll now get the memory dump. So let's go to the downloads, delete the old one, and get the memory dump. And here is our newly created memory dump, just gets downloaded. Okay, so now open the terminal using the Linux hex editor to make sure it's okay. So v86 memory.bin and find 00000500, and here it is. Okay guys, so which proves that we did everything properly. So we have A4, then we have FFFF, which it is, just splits by 4, but it doesn't matter really. So FFFF, and then 1F1100, and at the address of 530 we have the CCCC. Well, just the layout is a little bit different, but that's because we have only 16 bytes. So we have like 1, 2, 3, 4, 5, 6, 7, 8, and 8 words, or 16 bytes, and here we have 32 bytes in one line because of the layout is different, but the addresses match. We have the matching addresses, which is really cool. So yeah, that's kind of pretty much it. Okay, so in this case, so I'm really happy it works. Now one last thing, let's have a look at the size of the eventual executable. So if we have some free bytes to move encoding the word to somewhere else, just to make it a bit more prettier, so let's go to run.shell. Let's not delete the edit.bin, and let's run this stuff again. Escape from here and xxd edit.bin. So I just want to see how many free bytes. You must be kidding. Do you really mean we've used almost all of them? Yeah, I'm confused because I had a couple of extra bytes in my draft implementation. I thought that I can, if I don't do that redundancy, that I have some extra bytes. Doesn't seem so. Okay, so I need just 2 more instructions. I need to call and the return. So I just try to add 2 more instructions. So let's say call print string. Doesn't matter, it won't be working, but and return. Yeah, we have this minus, so we just don't have enough space for that. -2. So if we manage to shave a couple of bytes from somewhere, yeah, we could have shaved one here, for instance, and well, we might go for this sort of a trick. So here, and we might not print the space here. So this would save a few bytes. Save. And also yeah, now it should fit. Yeah, it does fit. Okay, it's not working now because, okay, but if I make like, so here I want to call, let's say, encode word. Yeah. And now if I take all this stuff, Control X, and here encode word and bring it here. And after just want to return. I'm wondering, is this still gonna fit? Encode word return undefined. Oh, whoa. Hold on a sec. Yeah, this is a little bit of an issue. Yeah. So return is undefined. So it doesn't mean that I need to duplicate, yeah, this escape. I don't really want to sacrifice it. Yeah, this one is needed really. And in that case, I'll need to duplicate this sort of a thing. Do I really need that? But hold on a sec. Yeah, I jumped return. Yeah, I still need it here. So, okay, I just want to see how many bytes do we have? If we have some more bytes, yeah, say jump equals to encode word, just to avoid that error. Okay, without this. Okay, and how many bytes? Okay, so it seems like we have 1, 2, 3, 4, 5, 6 bytes more, but that's probably not going to be enough to encode the return. Or is it? Is it enough? Oh my god, is this really enough? This is gonna be so cool. Oh my god, exactly 512 bytes. This is so cool. So here return jump equals to return. Now I want to make sure that the functionality is still working, okay? And if it does, and then we'll try to get rid of this one, for I believe that shouldn't be needed really, but we'll see. Run, so no errors. We are in there. Okay, so go into edit 0500. So it's like now we don't have some of these extra spaces, and let's say it's really tight. I like tight things. So let's say A40000FFBB, for instance, and we still have it. Okay, so let's say 0501 and reset the byte, and we are there. 0520. Let's take something like this. 05. Oh, so this is wrong. Okay, escape works. Edit. Hold on a sec. Yeah, I've just killed my operating system, so yeah, let's start from scratch. That's another thing to think about, but not this time. Okay, edit. So can I escape? Am I in the operating system? Nope. So yeah, escape doesn't work properly for some reason. Oh, that's because I need another for jump. But hold on a sec. Hold on a sec. I'm just wondering, guys, where is... Oh. Yeah, I actually... Why did I use return there? So copy. So why did I use return? I don't want to return. I need to go to shell. But this might result in -4 negative. Come on. Now if I get rid of this one, -2 negative still. And I'm not even sure if this is needed actually or not. Yeah, the address takes too much. Okay, what if I make exit, and here, what if I... Okay, so let's say I can put this one here and jump to exit, and jump to exit here as well. Well, you see, guys, yeah, it doesn't really seem to be possible because, yeah, I'm running out of bytes, and with the current implementation, doesn't seem to be working properly. So let's say I return here, would it be 1 byte only? So if I return from the encode word. Yeah, that doesn't work either. So if I could shave 2 more bytes from somewhere. Hold on a second, I just try to figure out if I can shave those couple of bytes. Okay, yeah, so it seems like I've just found an elegant way of how to do this. So I got rid of this hex symbols here. And this is a good idea because the actual physical address looks like this. So at very least, this is not exactly the proper way of representing the address. So I think this is just okay. And this was like 1, 2, 3, 4, 6, 7. So 16, also this saved another 32 bytes, right? So it's quite pretty a lot, which gave me an extra space to make a prompt like this. So enter address and then bytes. The new line and the prompt. So eventually, here is how it looks. So edit. So like we have enter address and then bytes. Okay, and we just do the same thing. So 0500 and let's say FFFF, and we have exactly the same functionality. So probably want so let's have a look how many bytes we have. Oh, sorry. So how many bytes do we have? Now we should have. Still don't have 3 bytes. I've exhausted them again apparently. Okay, so let's see if I have still. Well, this is gonna be -1 now. Yeah, -1. Yeah, I've exhausted the bytes with this. Yeah, but okay, how can I? Yeah, here's the trick. And then bytes. Edit. Okay. Okay. So let's say enter address, then bytes. So we fit in there, okay. Yeah, we now even have a free byte at the end, which is cool. Yeah, okay, so this is cool. So edit, yeah, enter address, then bytes. So let's say 05C0. And hold on a sec, I'm just wondering. Yeah, let's say FFFF, it works, but if I use the uppercase, it won't. Yeah, it won't. So let's say 05C0 and 0000. Yeah, it doesn't, because it converts. We do subtract the lowercase. We do subtract the lowercase a. So we need to either deal with. Yeah. So yeah, it's probably the least evil is just to make the address looks like this, which is not. I don't really like how it looks, but in this case we at least don't need to. Yeah, as far as we do use this lowercase for commands. Yeah, so because if this was like the uppercase, so the user might be wondering, so he needs to enter like this, but that won't work really. So to make it work, it needs to be like 0, 5, say A0 and some value, and here we go, right? Yeah, I think this lower, well, it doesn't look that fantastic with the lowercase letters. It would be more beautiful with the uppercase letters, but yeah, I think that for usability, for simplicity, it should be okay. So, and now also we have this extra space for this prompt. So we have enter address, then bytes. So the addresses are here. So yeah, say 0500, then bytes 3344, and here we go. Okay, guys. So yeah, I think this is it from my side. And I think we just end up here. Yeah, let me just add a couple more commentaries to end this properly. Yeah, this wasn't intended. The original implementation didn't have this, but I'm happy that we did come up with this kind of solution. So return to the edit loop. Okay, so encode word is now being separated, which is good. Okay, so here, print memory, we return to edit loop again, because we do call it from there, right? Print memory, yeah, from edit loop. And yeah, I've commented out this jump next loop because we really never get there, but it does store this does shave a byte, which is okay. So do we now have every single line being commented? It seems like, yeah. Okay, so one last test. Edit, edit, and 05C0FFAA. And here we go. Yeah, the address and the bytes being written there. Okay, guys. Yeah, now this is really from my side. I really hope you've enjoyed this tutorial series on creating a hex editor. So from now on, if we specify the proper bytes representing the x86 machine code instructions, this means that we can actually code. We can like manually input the bytes of the executable, right? And if we put instruction pointer, well, let's say we have some byte, a couple of bytes here. So let's say we put the instruction pointer here by jumping to this exact location. It would then start executing commands one by one until the end of the days, basically, or if it just finds a jump command back to the shell, or just stuck forever in an infinite loop. So it would start executing these bytes. But currently we don't have the functionality for that, and in order to get that functionality, we need to draft another command, the run command, which would be the topic of the next tutorial. And in the next tutorial, we'll make it and we'll try a hello world in machine codes that I've been demonstrating before, and we'll input the bytes for hello world program using this hex editor. Then we'll run it. We'll jump there using the run command, and hopefully, yeah, then jump back to the shell just to make sure that the entire stuff is working properly. So yeah, this is it from my side. Thanks for watching. Until the next time, and take care.